Let's continue with the CPU design. Now, there's not much difference in the actual CPU from the previous video. The only difference would be that the function here for the subtraction, addition, division and multiplication, I've actually generated the assembly language code for that, and we can actually use these now. So apart from that, the actual design here is just the same. Now the thing that's taken me a bit of time is building up an assembler. So I've built up an assembler for this CPU in Python, and I've never used Python before, so I've learned a lot of Python while building up this assembler here. Now the assembler is about 1,000 lines long, and it's taken me over the last couple of weeks to put it together. But I won't get into any details in the actual design of the assembler here. That would take me far too long to go through in this video, but I will go through another video at some point and I can get through the assembler. So if we were going to use the assembler, here's an example here. We just open up a notepad or any text file, and we can put in the origin of the program. So it's going to give the start address of the program, and any numbers that you put in, whether they be literal numbers or memory locations, you can put them in either in integers, or you can put it in as a binary, or you can put it in as a hexadecimal value. And whenever it goes into the assembler will convert everything to integer, and it will work with it all in integer, and at the end it'll output the results in whatever format you want. So at the moment I'm outputting it in hexadecimal so that we can load it into the CPU. So this little program here adds two numbers together and it sticks the answer in a memory location. So it's really quite simple. And it doesn't show you the full functionality of the assembler, because we can build in loops into this as well now, but it'll give you an idea of the what I've done over the last few weeks. So we're going to have the start address here. We can put in our comments, so anything after the colon's a comment and it gets stripped out with the assembler. And I've also added in the option here of putting in a couple of assembler directives. So the first directives we can put in is ds, which is define storage. Another one is dc, which is define constant. Although the name dc, define constant, is a bit of a misnomer, because you're not really defining a constant, you're defining a variable. And we can add in a true defined constant, which will be EQU, and I'm going to add that one in probably today. So we have the start address here, 20, and that's the start address of the actual data. And again, the assembler will add on to get the correct position here within memory. And the first value here, first, is going to be our memory location 21, and the next value, second, will be memory location 22, and the result will be memory location 23. And we're going to define the value 5 as hash 5, and define the value 3 as hash 3. So first of all, before we can actually do the addition, we're assuming that the numbers are actually in memory, but right now we're just going to have to stick them into memory. Okay, but normally with a program execution, the numbers would already be there and then you would be working with them, but we have to physically put them there first of all. So we're going to have the data 5 comma first, so it's going to replace these. Okay, so these are the labels. So everything that has got a number associated with it, we can use a label. So all of the literal values and all of the memory locations we can associate with labels, and the assembler will replace the labels with the actual values. So in this instance here, this would be data #5 and then a memory location. Okay, so what it does is it finds a 5 and it replaces the 5 with the #5 here, and it replaces the memory location here with the memory location that's generated here, which will be, in this instance, it will be the origin plus the start address of 20, and then it would be the one after that would give us the first value, the memory location that holds a value first, and the next memory location will hold the value second, and the next memory location will hold the result. So we've got those all sitting there, and this here just loads the value 5 into the memory location, it loads the value 3 into a memory location, and then we're actually able to start the program. So to start the program is we take the value of the memory location first into R0, which is 5, and we take the value second into R1, which is 3, and then we do the addition, and then we store the result R1 in the memory location called result, and it just ends it, and that just gives us the value 5 in one memory location, 3 in the next, and then result in the one after. So it's a kind of proper way that an assembly language would normally look. And once we've generated that, we can just run it through the assembler. So just literally run it through, and that's it ran through the assembler there. Now I've just outputted a few things here. So at the bottom here, the very bottom line here, it's just the actual assembly language code in hexadecimal. Okay, so that's all these lines here. And the very last one there is 5800, which is the end command. Now I've also, if we think about this assembler as a two-pass assembler, so the first pass deals with all of the labels and the looping, and then the declarations and any other assembler declarations or directives. And then the second pass will then take the actual language that we have, the actual assembly code language, and it'll map it onto the ones and zeros of our machine code. So at the end of the first pass, we're going to have a little output here. So I'll actually find it here for us. It's going to be down in Python. So it's going to be pass 1. So that's the actual output here. Okay, so it's taken our assembly language and it's popped this output. Now I've actually got to subtract these off. Okay, so there's a few wee bits and bobs there that it's easy enough. I can just delete this last lot off. But that's in effect the assembly language that we have here, and then we generate our machine code from that in the second pass of the assembler. Okay, so that's really how the assembler is working, and we can go on and we can load our values into the CPU. So we get the CPU, edit contents, and I can open up the file. And the file again, it sits in my directory there called Python. Now it outputs the file into a folder. This is the actual hex file, so it outputs it in as a hex file, and that's the hex file here. Okay, and that's our code that it's going to load up. So that's us loaded our program in here, and then we can run through a program. So it should take the value of 5, and then I think was it 5 and 3, add them together, and then save them in a memory location. So if I just let this simulate auto tick, so I've actually slowed this up so that you can see it running through. And we're going to have the value 5 is going to appear here, hopefully any second. So there we go, 5 and our 3, and then we do through the add command, which is 8, and that should finish it there. So that's it finished now. So if I was to dig into the memory location here, you'll be able to see if it's just slightly off screen here. I think I can make it just make it a little bit bigger. Okay, and I'll move it over here. So you can see here that it's put 5 in the memory, this memory location, the 3's in this memory location. It's added it together and it stuck the answer in that memory location. Okay, so it does work. The assembler works really quite well. And as I said, I've only shown you just a little part of what the assembler can do. So the thing that took me a little bit of time is to generate the loops. So we can actually go through and say, for example, I can put in loop 1, okay, and then I could come down here and I could put something like loop 1, okay. So it'll jump from this. Actually, if that was a jump command, say for example, so all of the loops would be used in the jump instructions. So I could get down to this jump instruction and it'll say loop 1 and it'll jump back to this position here, and I can jump all over using these this looping structure. So that's really what I've been doing over the last few weeks. Now another thing that took me a bit of time was building in the actual microcode. So you can see here, these are all of the commands that I have here. Okay, so we've got 4 store commands with 4 jump and jump subroutine, push and pop, move, and shift right, left, and or. And we've got the jump ifs, and at the bottom here I've added in the extra ones, which are the subtract, multiply, and the divisions. And of course we've got different addressing modes for each of these. And you can see here there's an addressing mode here. It says load array +5, so it's an indexed addressing mode. And we've got load and then brackets array. And we've got a post increment here as well. It's store array, RB plus with a plus at the end. So there's different addressing modes here. And what I've found is, as I've started building up some of the assembly language, I've decided that some of the addressing modes are a bit redundant for certain instructions. So I've just replaced them as and when I want to. And the process of replacing them goes on via this spreadsheet here. So in effect, we've got all of the outputs from our microcoded ROM here along the top. I'll get rid of that split. Okay, so we've got all of the outputs from our microcoded ROM along the top and just all of our 0s and 1s, and we've built up the code. So for example, in order to add in the last lot here, which were the multiplication, subtraction, multiplication and division, you know, I just had to copy and paste, for example, the AND logic in here, and then just change the actual values that we put into the arithmetic logic unit for choosing the division. Okay, so but anyway, I'll talk through that when I actually put the course together. So this program here allows me to generate new instructions, and I can actually generate the instructions by again adding the values in, and I can click generate the hex, and it will go through, and it takes about 5 or 6 seconds to generate all of the hex values that we use in order to populate the little compression ROM. And I can click here and it will output the file for the compression ROM, and I can click this one here and it'll output the file for the actual microcode, and those get loaded into the CPU and they get loaded in down inside the control unit down in here. So they get into the compression ROM here and also the microcoded ROM here. So it's been a mixture of learning Python and generating the assembly language, and also generating the code here for all of the instructions. And you can see that this is about, I don't know what, 500, 600 lines long. Okay, and every single 0 and 1 here, you know, had to be populated by hand by me, and I had to work out the process. It's in effect, it's register transfer logic, and I had to work out the logic of transferring the information from different parts of the CPU. So for example, if I built up a complicated instruction, something like shifting the information from one memory location to another memory location, then I would have to go through a whole process of first getting the actual address of the memory location and bringing it into the CPU, and then going getting the contents, and then moving it into a register on the CPU, and then getting the next memory location into the CPU, and then taking that value and shifting it back into the memory location. And it gets confusing, and it takes a little bit of time to work out the transfer language. But those are the two main things that I've worked on, which is this, which is really pretty much complete. And I'm very quick now at changing it and adding extra commands or changing the commands. And the other thing has been the assembly language code itself. So again, I've had to learn Python in effect from scratch so as I could build up this code. And now my little dirty secret I have is I didn't just do this by myself. I used ChatGPT. So I'll go through another video of how I used ChatGPT in order to help me generate this. But it wasn't just a case of me saying to ChatGPT, which is an AI chatbot, it wasn't just a case of me saying, go build an assembler for me. You know, it still took me, you know, over 2 weeks, 2.5 weeks of quite a lot of, you know, hitting my head against the wall and the usual sort of thing that you do whenever you're learning a language, an awful lot of trial and error. But it's been an invaluable tool, and it's been it's been fun using it. And it doesn't always get everything right. Sometimes it makes logical errors, which is a bit strange. But I'll talk about that in a different video. But anyway, I've managed to build it up and get it all working, and I'm quite pleased with it. And I feel like I've kind of got over a hurdle, because 2.5 weeks ago, the idea of me having to build an assembler, you know, with 1,000 lines in Python from scratch without knowing any Python, it was daunting, you know. And sometimes the Python was really frustrating because it's an indented language, and my indents were wrong, and I was having to try and fix them. And but once you get used to that, it was a lovely language to use because it's got really nice functions within it, you know, built-in functions for converting from hex to integers or binary to integers, and also for doing any manipulation of strings, which is really what an assembler is to a large degree. It's a manipulation of strings. So it's been great using it in the end, apart from the indentations. So I've rattled on enough with this video. I'm going to crack on with this, and I'll build in a few more interesting programs. And as I build in the more interesting programs, I'll probably find that I've got commands that I don't really use, or ones that are missing, but I can get in and change them and build on them quite quickly. And I'm hoping whenever I put the course together, it gives whoever's doing the course the confidence to go in and build their own commands, to decide, well, I don't want this instruction set, I want a different instruction set. And you can go and you can use the Excel spreadsheet, and you can change this code here as well. I'll make it so it's relatively easy to change, and you can just build your own. Okay, that's the idea. So that's all for this video. Thanks for listening. I'll get you now. next video. Goodbye.